them were still much slower than the other languages. And all of these appear to be exploitable over the LAN, but not the internet. We're dealing with 43 to 144 nanoseconds average per byte. In more detail, the array equals, sorry, that's actually backwards. Array equals byte was actually was slower than string equals. That's correct, actually. So string equals, for instance, for individual bytes, we looked at what does it do for the first byte and the second byte and the third and fourth. And string equals is pretty fast. It starts off a little quicker than others, about 9 nanoseconds for the first byte difference, and then 88, 30, and 34. But it was still much faster than the array equals. The worst case was array equals with object arrays. And if you don't have a byte buffer you're passing into array equals, it'll actually devolve to an individual method call on every object, basically saying if object 1 dot equals object 2, go to the next one. If object 1 object equals object 2. And that's the worst case. Now, we didn't find any libraries that actually used this particular method, but that's something to avoid if you're an implementer. Looking at the array equal behavior, we were wondering why it seemed to be faster than string equals. And what we found was an interesting thing where it appeared to have this sort of stepping behavior between the first, second, third, and fourth bytes, where it appeared that every 16 bits, it would be slower, and the subsequent byte would be faster. And we think it's possible. We haven't analyzed in detail or disassembled it fully to understand why, but it appears to be fetching data in 2-byte quantities. And this is most visible at the full clock speed, where it takes 80 nanoseconds for the first byte, then only 5 for the second, then 80, and then 5. And this can actually help an attacker later on. We'll talk about that. Another interesting thing we found was that Base64 compares, we think they're more vulnerable than just a regular comparison of the binary data itself. And if you look at some of these libraries we looked at, some of these web frameworks, that often they'll compare the Base64 encoded value, the Base64 encoded string, against the other Base64 encoded string. And with Base64, as you know, you're taking 8 bits and you're cramming it into 6 bits. And so this is great for sending an email or over a text interface, but it's not so great if you're trying to avoid easy exploitability for attackers. So in this case, this actually gives attackers a 4 times advantage because you're revealing 6 bits for every byte the attacker tries to guess. And so they only have to try 64 values before advancing on to the next one. Also, there's an additional timing leak that Base64 encoding offers, where if you're taking a secret value and encoding it Base64, it will branch differently based on the value that you're encoding, whether it expands it into a subsequent byte or not. And so in this case, you're leaking approximately the Hamming weight of all the bytes that you're encoding during the encoding process. So we didn't attack that, but that might be something to look into later. All right, so now let's take all this stuff we've learned. We've looked at different vantage points, and we've said, what's the different delays? And we'll have some thematic music for this from Star Wars. Thanks, Felix. I'll come to your talk later. All right, so yeah, so we've looked at different vantage points, and we said, what delays are visible from different vantage points? We've looked at different languages and said, hey, what looks exploitable? So we've looked at Java and said, hey, Java looks exploitable from the LAN. It's from 40 nanoseconds varying up to 180, depending on how fast you're... All right, this is great. I love it. Yeah, so we've looked at different vantage points. We've looked at different compare functions. And let's look at actually attacking HMAC. So a little more background on attacking HMAC. Some of the first attacks against HMAC were documented in 2007, and in terms of timing attacks. So the first one that was publicly released was an attack against the Xbox 360 bootloader. In this case, the Xbox 360, during its bootloader process, would verify an HMAC on a particular bit of code and then decide whether or not to run it or not. And in this case, based on whether the HMAC was correct or not that the attacker had supplied, each byte would take additional 2.2 milliseconds to compare. And this is very visible from local, since you have full physical access to your game console. Another announcement was in the Google Keysar library, which is a multiple language implementation of various cryptographic things for web toolkits. And it had a timable HMAC comparison. Then Sun's JDK6, message data equals function, Java Bouncy Castle, Mozilla's NSS TLS session ticket, which we'll talk about more in a minute, and then finally an OAuth 1.0 HMAC verification. That was actually Sebastian Martini. I got the name wrong on that one. So exactly what is an HMAC and why would it be vulnerable to timing attacks? So in this case, what happens is a server will generate a token for the user. In the most basic case, this is used for things like session IDs. This is used for like single sign-on. It's used for OAuth, OpenID, and other processes where you want to give the client something which they can't modify. So the server wants to generate a ticket for the client. They want the client to give it back to them unmodified at some point in the future. If the client does modify it or try to forge it, you want to know about it. So what you do is you take a hash function, and hash functions aren't normally designed to work with secret keys. So you use a construction called HMAC, which combines a bunch of data and a secret key and gets a hash result from it that's a keyed hash result. You take the ticket you want to sign, and you apply the HMAC with your given server secret key to that data, and then you append this authenticator value to it, basically like a signature. And then on the validation side, why this would be subject to timing attacks is that the server has to generate the correct HMAC for a given message in order to compare them and see if they're not equal. So on the server side, you know the secret, right? The attacker supplies you a message, or the legitimate client. You calculate the HMAC using the correct key over this ticket, and then you just compare the two, right? If they are the same, then the ticket was unmodified. If they're different, then someone's messing around with you. So web authentication frameworks. Anyone here familiar with OAuth, OpenID? You use them? Anyone implemented OAuth or OpenID? There's quite a few implementations out here. So these frameworks allow two different things. They have two different purposes. OAuth was designed with the purpose of allowing a client to authenticate themselves to the server to access various APIs on the server. So the client and the server actually share the same secret, and the client can send requests to the server, like delete my Flickr photo album or whatever. And you sign it with an HMAC, and if the request validates, then the server says, sure, this user has this correct HMAC. Go ahead and do whatever they asked me to do. This is used all over the place. Pretty much every web API that allows the client to sign some kind of requests has a mode of allowing HMAC. OpenID is slightly different. OpenID is a way of allowing a user to authenticate to one website with another website performing the authentication for the relying party. So in this case, the third party basically signs a token that says, yes, this user logged in correctly with their password. Go ahead and let them into your site. So those are the two different methods of using OAuth and OpenID. And like I said, they're both, OAuth is more common and is growing in volume. OpenID isn't used as much, but is supported by a lot of people already. So we went and actually reviewed the source code for these implementations and found a lot were potentially vulnerable to simple compare timing attacks. Basically, everyone who looked at these things and said, hey, we've got two values. We're going to check if they're equal, the correct HMAC value and the one the attacker or client supplied us. Let's just do equal equals or string.equals or arrays.equals on them, and that's our result. We actually found that dozens of implementations were vulnerable to this. And when we notified them, some decided to fix it and some did not. So exploiting timing attacks. We implemented a number of different ways of exploiting this. The simplest way we came up with, which we haven't seen anyone else do yet, was to iterate over the byte that you're guessing. And you generate a bunch of samples for a particular byte, sending it to the server. You measure the time that it takes, then you iterate over your guesses. If you're lucky, it takes on average about 128 guesses per byte, because since there's 256 if you're unlucky. And what we did was we implemented an approach called iterative guessing. Whereas you remember before on the Java arrays.equals, for instance, you have a mechanism where the first byte that's correct takes 80 nanoseconds longer, and then the second one takes 5 nanoseconds, then 80, and then 5. So the second one is much more difficult to distinguish than the first one. But what we can do is iterative guessing, where you walk forward past it, you take the best guess at a particular level of samples, and you assume that's correct. Then you move forward from that and try it against the next guess. And if you get a confirmation, then you'll see an even wider difference between the two distributions. If you got it incorrect, you won't see any difference between the two. And we found that's actually successful with a lot of systems like this where there's a small number of multi-byte variances between things. It doesn't work, for instance, if you have a 32 or 64-bit compare, because you'd have to be generating 4 billion different values for each sort of incorrect guess you walk forward with. We didn't go out and attack production websites, just to be clear. We did not attack Google or Amazon or others. Instead, we just sent them an email saying, hey, we found these flaws in open source implementations of these toolkits, and you use similar things. Why don't you just check your own servers for it? And we figure that if they wanted us to test it, they would have asked us to. And if we tested it without being invited, then they might consider it an attack, where basically we're generating lots and lots of invalid requests. If they happen to see this, no one actually logs incorrect HMAC results, but if they did see this, they might think that we're trying to attack them. And also, we don't own the server, so we don't have permission to that. So it's up to them to review their own code. And at least one major provider that wasn't listed above actually confirmed that they are vulnerable and that they used a common open source implementation. So they are in the process of fixing that, and hopefully it should be deployed already. Countermeasures to timing attacks. The naive countermeasure most people come up with when they first hear about it is let's add noise. If you follow some of the threads that are on the OpenID list, some of the first things people said is, well, we'll just add random delays or whatever. And it sounds good at first. So you're looking at a graph and you're like, hey, it seems like we can do something about this. So let's start with the first. This is without noise. And then we add a bunch of noise for a certain number of samples. So we say, here's 500 samples with, I think you added between 0 and 1.5 milliseconds of noise to this randomly. Sorry, 150 nanoseconds of noise to each of these. So on the order of the delta between them, we basically could double the value or add nothing to a value depending on the random choice we made. So as you can see, this distribution looks pretty random. And more importantly, you can't distinguish the black from the yellow, right? There's a lot of overlap where it's brown, but there's no clear distinguishing factor. But let's just take some more samples. So while still adding noise, we increased it to 1,000 samples. As you can see, the distributions are starting to look more like they did originally. And then we took 5,000 samples. Again, these still have noise added to them. But as you can see, the two peaks are starting to separate out clearly. There's kind of an outline of black on the left and an outline of yellow on the right. And then finally, with 10,000 samples, as you can see, you have almost identically to the original distribution. So adding noise does not do a good job of preventing timing attacks. It only requires the attacker to take a few more samples. A fix that we recommended to a lot of people on these mailing lists was a simple constant time compare loop. This used to be an interview question we would use, but since we revealed it to everybody, it's no longer an interview question. So this is in C, but the equivalent works in Python or Java or whatever. Basically what you do is you check the length first, and then if you walk through all the bytes in the array and you just compare them and you XOR them together. If there's a difference between them, you'll get a non-zero value, and if there's no difference, you'll get 0. And each time you accumulate using OR. So the important thing about this code is that it doesn't generate any conditional branches that are varying based on the secret data that you're comparing. And there's a few things about this. The first thing we got back from a few people was, hey, this is a lot slower in some of our interpreted languages. The particular example someone used was .NET. And what they were saying is, hey, in .NET, a normal comparison devolves to C memcomp. And this particular loop implementation, of course, is implemented in bytecode, and so isn't quite as fast. They found it was about, I think, 10 times slower than a memcomp. But if you remember, the memcomp probably is not your bottleneck on your server. If it is, you're handling a ton of requests, you probably need another server. And then second of all, it's probably better to not be exploitable than to be a little faster and insecure. Absolutely, yeah, definitely. The HMAC hashing operation takes a lot more CPU horsepower than the comparison. But depending on whether that's implemented in native code or not, it may vary. So that could be a problem, and it could affect some implementations, and it's worth some investigation, but we don't think that's a good enough reason not to fix this bug. So OpenSSL. I was set to put some slides in here, and I was trying to decide whether or not to put these in or not. So I decided to tell the story instead. Yes? Yes. By the way, we're going to have questions answered at the end as well. Yes, Sun did fix their JDK implementation in update 17, I believe.